Good evening. So, any questions? Okay. So today we'll be discussing the mechanics. So unlike fluid dynamics, so this syllabus is very short, right? So the syllabus, whatever it is there in this particular topic is, one is generalized coordinates, then D'Alembert's principle, and then the third one, Lagrangian equation, and the fourth one is Hamiltonian equations, and the fifth one is the moment of inertia. So these are the topics that we have as part of this mechanics topic, right? So in this actually, so most of the times actually the questions were asked from these three sections, right? So most of the times this is the place actually where the questions were being asked by UPSC, right? So here generalized coordinates, like actually the discussion of mechanics comes into picture, that is with the help of Newton laws actually we will be deriving all the force or actual mass or any movement related equations, right? So that is what we call as the classical mechanics. So the mechanics is completely divided into, so this is the classical mechanics. And then this is quantum mechanics. Right? So classical mechanics which obeys Newton laws. So this is the classical mechanics, and then here actually there are certain assumptions, that is law of conservation of mass is valid, law of conservation of energy is valid. So both together as a separate principle, those are valid in this particular case of classical mechanics. But coming to the quantum mechanics, so Einstein proved that E is equal to mc square, where here this is energy and this is mass. Now here actually energy is equivalent to a mass, or mass is equivalent to an energy. So based on this principle, there is a combined principle that came into picture, that is law of conservation of mass and energy together, right? So energy can be converted to mass or mass can be converted to energy. So that study is the quantum mechanics. Now in the classical mechanics itself, whatever we are going to study till now, right? So as part of your engineering or the +2 syllabus, everything whatever you studied is only with no constraints or minimal constraints actually we have derived. Suppose if there is a sphere like this, now in this particular sphere, suppose if there is a ball that is thrown, then you are forcing this particular ball to go in this particular circular manner. If this sphere is not there, this ball would have traveled in this particular path, correct or not? So you are subjecting this ball to go in this particular manner. Like this actually, if there are some constraints that are coming into picture, that is the ball is subjected to move only along the spherical direction. That means here actually x square plus y square plus z square is equal to a square. So this will constrain the ball to move in a specific direction. So this constraint is coming into picture. And then when these kind of constraints are coming into picture, so Newton's laws will be a little bit difficult to solve, right? So there actually a new methodology of bringing in the same equations whatever we derived with the help of Newton's laws. That is, in case of simple harmonic motion, if you notice, that is, so the time of a simple harmonic motion, right? So square root of L by G 1 by 2 pi times of. So this is the simple harmonics time period equation which we have derived with the help of Newton's laws itself. But actually, so this simple harmonic motion equation, the same equation, rather than considering the mass or the acceleration, there is a new concept called the energy is considered to derive the same equation. Got it? So here actually, as part of Newton's laws, whatever we do is we start with the displacement, and then the extension of the displacement, actually we make it the velocity, which is nothing but the time derivative of the displacement, and then the extension of this is the acceleration, which is the time derivative of the velocity, and then so this acceleration getting multiplied by mass. So this we brought in, this is what is the second law of motion, that is F is equal to ma. Based on these constraints, whatever we have talked about at this particular place, that is displacement, velocity, acceleration and mass. So these are the fundamental quantities along with the time to derive all the kinematics related equations or the mechanics related equations, right? Correct or not? So whatever we have derived, right, in as part of statics or dynamics, we will be using only these particular values: displacement, velocity, acceleration and mass and time. So these are the only variables that we are going to use it as part of our normal mechanics equations. But rather than this, so the energy equation, if you brought into the picture, then this usage of energy to derive the same phenomena, whatever we derived as part of simple harmonic motion or any kind of random motion. Suppose if there is a rolling motion, that means if there is a slant, then there is a ball left it here. So this is going to travel in this particular direction. So that is subjected to the constraint of this particular path. So all these constraint related motion equations deriving with the help of Newton's equations is very, very tough, almost impossible. So there, if we consider energy as the variable there, then you will be solving the same equations with a minimal effort. So even though we have lot many constraints for the particle to move, all those constraints taken together into a single format and then bringing into the energy equation, and then there is something called Lagrangian L, or there is something called Hamiltonian, so which are related to this energy. And so this is Lagrangian is derived, this is based on the kinetic energy minus the potential energy. So this is how actually we bring in, and we will be doing certain calculations based on the calculus, that is dou L by dou Q and dou L by dou Q dot. So those things actually we will be using to solve the same mechanical equations, right? So this methodology we call as the Lagrangian or the Hamiltonian equation. So Lagrangian equation and Hamiltonian equations are one and the same. So not much of difference except for this energy equation, Ke minus Pe or Ke plus Pe. Based on that, actually we will be deriving the classical mechanics equations when there are so many constraints that are present. Got it? So that constraints will make our problem statement very, very complex, and those complex equations can be solved with the help of normal Hamiltonian or Lagrangian equations, where the UPSC is focusing in that particular area. Got it? And along with that, so very well known moment of inertia. So this is very, very easy, and then most of you people might be already known about moment of inertia. So this is one part of your syllabus, and then this generalized coordinates will play the key role in identifying the Lagrangian or in identifying the Hamiltonian. So this L or H will be derived based on the generalized coordinate. So we have to understand what is a generalized coordinate system, and those generalized coordinates whatever we derive, right? So those generalized coordinates are going to be used in L and H. So all these things together will be of the same topic. Generalized coordinates, Lagrangian equation and Hamiltonian equations are one and the same. And then D'Alembert's principle is a little bit different from that. This D'Alembert's principle is going to be used to, so that is, so when a body is moving relative to the other body, now the relative mass is getting moved. Now actually, so this one is discussed separately, and the last one is, this is the moment of inertia. This moment of inertia is, so this is very, very easy, right? So this moment of inertia is nothing but a mr square, sigma mr square value. We will be calculating it. I will explain in detail in today's class itself. So what is this moment of inertia, how we are deriving this moment of inertia, and what is the advantages of moment of inertia. Got it? So this is briefly a small syllabus, and it won't take much of the classes, right? So within short time actually we are going to finish this entire syllabus. So I think one question is expected from this by UPS. Got it? Any questions on this? Any questions? Okay, so you can note down this. Okay, right? So we will start with the simplest topic, moment of inertia. So moment of inertia can somebody tell me what is moment of inertia? From where this is coming for us? Anybody? So when we initially define the classical mechanics, there is nothing like moment of inertia at all. But to make our work very simpler, so we have brought into the picture, that is this moment of inertia externally, to make our work simpler. So ideally there is nothing like moment of inertia. Yeah. So but actually where we have brought in that distribution of mass from axis of rotation, right? So what is the impact of it in our analysis? So let me explain that. So here actually the idea of moment of inertia coming into picture from the fact that we are very well aware of Newton's laws, and then those Newton's laws will give very excellent phenomena for us with the help of calculus to solve any kind of moment equations, right? That is, if there is a particle that is traveling at any position, you will be able to find out what is the location of the particle and with what velocity it is traveling, with what acceleration it is traveling, and what is the energy associated with that particle, what is the kinetic energy part of it, and what is the potential energy part of it. So all these things together we call as the mechanics, right? So the mechanics actually plays the critical role in this. One is the displacement, another is velocity, another is acceleration, another is mass, another is energy or momentum, energy, and this energy is further divided into potential energy, the next one is the kinetic energy. So along with this, so for deriving all these things, there is a factor called time factor. So the study of all these things we call as mechanics. All these physical quantities is called as mechanics, right? And this study is carried with the help of Newton's laws. So this Newton's laws, we have three different laws. One is law of inertia, and then law of moments, and then so action and reaction. So these are the three different laws. Almost everybody is aware of it, right? So those laws actually, with the help of Newton's laws, will be calculating all these things. And this study pertaining to the movement of any particular particle is called mechanics. Now, if it is subjected to some constraint, then with the help of same Newton's laws, it will be very tough. So in such cases, we are going to Lagrangian or Hamiltonian. And then the study of all these things. So there are two different kinds of motions usually. So that is, one is the linear motion. Another is the circular motion. And then the third one is the general motion. So general motion is nothing but, so if I say that if this particular charge pace is moving like this, then here this position is changed to a different location here now. So there is a linear displacement from here to here, and then there will be a circular way also, right? So that means starting point to the ending point, so there will be an angle difference. If I take from, suppose this is the origin, and then initially the particle is at this particular point. Now actually this is moved to this place. That means there is a linear displacement from here to here, and there will be a circular displacement or the angular displacement from here to this particular point. Let us say this is how it is. So see this kind of. Now there is an angle between these two. Now in such kind of cases, so one is the linear motion and another is the circular motion. So these two together, any general particle will be having, and only these kind of motions any general particle is having. Now the study of the linear motion is very easy with the help of Newton's laws. And the same study, if you wanted to carry forward to the circular motion, then you have to, for each and every aspect, you will have to identify an analogous from the linear motion. So all these things are pertaining to the linear displacement, linear velocity, linear acceleration, linear mass. Sorry, this is mass is anyway quantity, and then momentum is linear momentum, and then this energy is a scalar quantity and time is a scalar quantity. Now all these things are actually pertaining to the linear motion we will be calculating with the help of Newton's laws. Now the same discussion or the same analysis, so if you are able to intelligently adapt to the circular motion, then your work will be much more simpler. So from that idea of using the same analysis of linear motion for the circular motion, so there is a new quantity called that moment of inertia coming into picture. Now let me explain how it is going to be. Just note down these things. Note it down. This is actually the mechanics. Okay. Now, corresponding to this, I think there is one more. There is something called force also is there. Force. Now, this is linear. And then correspondingly we will be deriving for rotatory motion or the circular motion or angular motion. So corresponding to the linear displacement, that is we have angular displacement. That means suppose we say that in linear displacement this particle from point A to point B it is moved. So from point A to point B it is moved. Then correspondingly if you have a circular, so that means if the particle is point A and then it is moved to point B, then we say that it moved an angular displacement of angle theta. Right? So this is the angular displacement, this is the linear displacement. So it is having an angular displacement of theta and this is having an angular displacement of x. Sorry, this is having a linear displacement of x. This is how we will be representing. Similarly, the velocity we have correspondingly there is something called angular velocity. So this is, sometimes it is represented with d and this is represented with theta. And then the velocity, or this can be even represented with x. So velocity v can be represented as the derivative of the displacement with respect to time, dx by dt. And correspondingly the angular velocity is represented with omega, and this value is given by d theta by dt. And then the acceleration is dv by dt and is represented with a letter called a. And here the angular acceleration alpha is represented as d square theta by dt square, or this can be represented as d omega by dt, and this is what is called as angular acceleration. This is angular acceleration. And then, so here comes the mass. The corresponding quantity of mass is the moment of inertia in angular displacement. So why it is going to be that way is, let me explain. See this, whether it is vector or scalar, that depends on the nature of the physical quantity. It's not that entire mechanics quantities are scalars or entire mechanics quantities are vectors, right? So that discussion comes only based on the type of quantity. Suppose if you take displacement, so that means there is a positional change from point A to point B. So this will be a straight line. That means it is having certain associated direction to it. That means this position change to this position. That is, this is the displacement which we call as a vector. Now the derivative of that is in this particular direction with what velocity I am moving is nothing but the vector quantity again in the direction from A to B. So that is also a vector. So this is also a vector and this is a vector, and similarly time derivative of velocity is again a vector, and mass is a scalar, and force is a vector, momentum is a vector, energy is a scalar, and time is a scalar. Got it? So some scalar quantities are there, some vector quantities are there. That depends on the nature of the physical quantity. That will be decided. Got it or not? Deepak? Okay. Fine. So now actually corresponding to the energy, so or the kinetic energy, when there is a linear movement from point A to point B, so with certain associated velocity, then the energy of that particular, so the kinetic energy of the particle whichever is moving, so this is given by Ke is equal to half mv square. Ke is equal to half mv square. Almost everybody is aware of it, right? So this is the kinetic energy associated with the particle when the particle is moving from point A to point B. Now, I wanted to develop the kinetic energy equation in rotatory motion. So for that, if it is easy for me to remember, or if it is easy for me to analyze easily, if I have the same kinetic energy in case of rotatory motion as of some quantity into omega square. Got it or not? So of m is the mass and v is the velocity. So corresponding to the velocity, linear velocity, there is an angular velocity we have defined. And then half is as it is there. And in place of mass, if there is some equivalent, because this is radians per second is the omega units, and velocity equation is meters per second. So there is a huge difference between meters and radians. So radians represents the angle and meters represents the length. Now dimensionally it should be equivalent, and then it should not disturb the original sanity of the energy equation, but you wanted to derive in this form of half something into omega square. Now what is this something? And that's what is thought through. Now here actually half mv square. Now m actually, so Ke in rotatory motion is nothing but half mv square. So but actually the relation between the linear velocity and the angular velocity, that means suppose if it is rotating with a velocity of omega, that is omega is equal to d theta by dt, and then correspondingly this value, if you notice, it moved an arc displacement of r theta, where r is the radius, correct or not? And then r theta, this is moved from point A to point B in the same time, angle is changed from 0 to theta, correct or not? Understood? So this is the displacement. Let us say P equal to r theta. Then dP by dt is nothing but the linear displacement from point A to point B. Now this is nothing but r into d theta by dt. But d theta by dt is nothing but omega, and dP by dt is nothing but the linear velocity from point A to point B. That means V can be expressed as, this is the linear velocity, V can be expressed as r times of omega. Understood or not? Is this understood? right? So V can be expressed as R times omega. Now here this kinetic energy equation of M into R omega whole square. So here of M into R square into omega square. Now if I wanted to correlate to this equation of into M into R square, if I keep it there, then omega square. Now actually I have brought into the format of something into omega square. Of mv square is brought into the form of something into omega square. This is the angular velocity and this is the linear velocity. Got it? Now here this can be treated as of I omega square. And this I is the important factor what we are going to discuss, which will occupy one particular topic for us, that is the moment of inertia. Got it or not? So this entire discussion is meant for only one simple fact, that the linear analysis you wanted to add up to the circular analysis with the corresponding analogous quantities. So the analogous quantity of mass in case of circular motion I. So this I is nothing but the moment of inertia. Understood? Understood or not? Okay, so you note down this. Yeah, so you note down this. Then actually why? So there is something called sigma comes into picture. I am going to explain that. If you note down this. Done? Okay. So this is the only reason why there is something called moment of inertia defined at all. So you wanted to analyze with the help of linear analysis. And then one more important factor of this finding out the moment of inertia is, so we are talking about the circular motion. Now in this circular motion, let us say this is one iron block, and this iron block is rotating about a central axis like this. Now this is trying to rotate in this particular way. Here, if you notice one particle at this particular point, and this particle is having, let us say, m1 mass, and then this is having a radius of r1. Then m1 r1. So this is the equivalent moment of inertia for one particular particle which is located at one location. That means here for this particular particle m1 r1 square is the moment of inertia. So why we are separating this into small particles is each particle is located at a different radius. So that means if I take one more particle here, this is having r2 radius and this having it is a m2 mass. That means plus m2 r2 square. And then if you divide to infinite particles, all the particles together, it will make sigma mr r square or sigma mr square. This is nothing but the moment of inertia of any random body taken. Got it or not? Understood? So because each particle is located at a different position, so each radius is different, corresponding moment of inertia at that particular location dependent on the radius, hence you have to average out the entire moment of inertia. So that is each particle and then each mass, each particle location and its mass. So correspondingly mr square you have to calculate it. For the entire body you have to calculate the moment of inertia. Now the moment of inertia is different, so we are talking about the circular motion, right? Now this particular line, if I take it, this body can rotate about its own axis like this, or this particle, so this particular block can be rotated in this particular format like this, right? So anything can happen. So this moment of inertia is dependent on the axis about which it is trying to rotate. Got it or not? So suppose if I say that this body is rotated about this particular line, then earlier it is R1. Now this is R1. That means if it is rotated with a different axis, then definitely the moment of inertia is going to be changed. So it will be completely dependent on the type of rotation it is having and the place of rotation it is having. Got it? So that's what is the moment of inertia. So for a simple body, we have to calculate the moment of inertia based on the fact that about which axis it is trying to rotate. Now in this moment of inertia, we have two different theorems. One is the parallel axis theorem, and another is the perpendicular axis theorem. So this parallel axis theorem and perpendicular axis theorem both are coming into picture only for the fact that for different kinds of shapes you wanted to make your work simpler. So the calculation of moment of inertia will be a little bit easier. Our work will be reduced to a greater extent with the help of these two theorems wherever it is applicable. So we have to understand what is this perpendicular axis theorem and what is it parallel axis theorem, right? So here the perpendicular axis theorem is straightforward and easier. So what it says is, suppose if there is a chalk piece like this and this chalk piece is trying to, let us say this is one axis, this hand is one axis. So this is rotated like this. So like this actually it is trying to rotate. That means there is a moment of inertia for this particular chalk piece, and let us say this is x-axis and this x-axis. So I call this as, this is x-axis and this is y-axis, and the body is located at this particular point. Now when it is trying to rotate in this particular format, then the radius is this way, right? Then the moment of inertia of this particular body, let us say call as Ix, because it is trying to rotate about the x-axis. So Ix is nothing but sigma m into y square, right? Sigma m into y square is nothing but Ix, because this location is y, right? This is the moment of inertia, so with respect to y. And then the same body, if it is trying to rotate about the y-axis like this, so this is how actually if it is rotating, then let us say the moment of inertia of this particular body is Iy. So Iy is nothing but m into same mass, so m into x square. This is the moment of inertia about y-axis. Now the sum of these two, now actually I take the third axis as this one, that is, if I take this particular axis which is perpendicular to both x and y, which is nothing but the z axis. So here Iz is nothing but Iz is nothing but, so this is the radius, so sigma m into r square, but r value is nothing but, this is x displacement and this is y displacement, then this is x and this is y, then the point location, let us say this is x comma y, then so this is sigma m into x square plus y square, and this will make us sigma m x square plus sigma m y square. So this is Iy plus I is Iz, and this is what is the perpendicular axis theorem. Got it? So what perpendicular axis theorem talks about is, if there is a mass m, if it is rotated about an x-axis, and then let us say the moment of inertia of the body with about an x-axis is Ix, and the moment of inertia about an axis which is perpendicular to the first axis is, let us say, Iy, then the moment of inertia of the same body about an axis which is perpendicular to both the axes will be sum of the both. Got it or not? So the perpendicular axis theorem what it says is, let the moment of inertia of the body about any axis Ix, and the moment of inertia of the same body about an axis which is perpendicular to the initial axis, about an axis which is perpendicular to the initial axis, then the moment of inertia of the same body, about an axis which is perpendicular to both the axes will be sum of the moment of inertia about the first two axes. You can note down that way. Got it? This is the perpendicular axis theorem. Noted? See this. So, let the moment of inertia about an axis is Ix, and the moment of inertia about an axis which is perpendicular to the initial axis is Iy. Then the moment of inertia of the same body about an axis which is perpendicular to both the axes will be sum of the first two, so sum of the moment of inertia about the first two axes. Got it? Understood, Rishi? Okay. So this is the perpendicular axis theorem, so which you can easily identify the moment of inertia without calculating about the third axis by adding the first two. And then the parallel axis theorem. So parallel axis theorem, so suppose if you know the moment of inertia of this particular body about its own center of gravity, so this is the moment of inertia. Okay, so let I be the moment of inertia of a mass m about its centroid or about an axis passing through its centroid, then the moment of inertia about an axis parallel to the axis passing through the centroid will be I parallel equal to I plus md square, where d is the distance between the parallel axis. And m is the mass of the body. So this is the parallel axis theorem. centroid and center of mass are one and the same. Yeah. Got it? So center of gravity centroid, center of mass. For all the practical purpose, all these three are treated as same. But a little difference is there between center of gravity and centroid. The difference is centroid talks about only the mass, entire mass is concentrated at one particular location. But centroid talks about the weight of the body is where it is concentrated. So mass and weight, that means G is coming into picture extra. Got it or not? So that is the little difference. But usually whatever the bodies we are going to deal with, all are homogeneous masses. Homogeneous masses means the mass is, the density of the mass is same across entire body. So if that is the case, then the centroid and the center of mass or the center of gravity is everything is same. Suppose if the density is changing, then the center of mass and the center of gravity are not one and the same. Got it or not? So, but practical purposes, we treat everything is same. Okay. Got it? So, did you understood this parallel axis theorem? Let me expand this parallel axis theorem. Now, actually, if this is the mass and this mass is having m as the mass, and then you know the center of gravity, so you know the moment of inertia of this body about an axis which is passing through its centroid. Now passing through the centroid, it makes a lot of difference. So let me explain how it is passing through the centroid. Take this. So take this chalk piece box, and then the center of gravity is located at the midpoint. And then with respect to height also, it is located at the midpoint. Now an axis which is passing through the centroid, that means this can be this axis, or this can be this axis, or this can be with a certain angle also, it can be the same axis, but it is passing through the centroid. So as long as it is passing through the centroid, any angle it can pass through. Got it or not? So even it can pass through like this also, it can pass through like this, it can pass through like this, but it has to pass through the center of mass, which is located exactly at the center, where the mass is located. Got it or not? So you know the center of, so you know the moment of inertia of this particular chalk piece box. If it is trying to rotate like this, or suppose if this is the axis, if it is trying to rotate like this, then you know the center of gravity, you know the moment of inertia of this particular body. So if you know the moment of inertia of the body, if it is rotated about an axis which is perpendicular to the center of gravity, so about an axis which is passing through the center of gravity, then you wanted to find out the moment of inertia of the same body if it is rotated about an axis which is parallel to the axis which is passing through the centroid. And then this is how actually it is trying to rotate now. So earlier it is trying to rotate on its own like this. So this chalk piece is rotating on its own. Now if I know the moment of inertia of this particular chalk piece when it is rotated about its own axis like this, then I wanted to find out the moment of inertia of the same body or the same chalk piece, but now it is rotated like this. Got it or not? So earlier I know the moment of inertia of rotation like this. Now actually I wanted to find out the moment of inertia when it is trying to rotate like this. Now in such cases, if you know this as I, which is the moment of inertia of the body about its own axis, then the moment of inertia when it is trying to rotate about my hand like this, then initial I plus, then the mass of this particular body multiplied by the square of the distance between the center of gravity or the axis between these two. So that's what is the parallel axis theorem. Understood? Understood or not? Right? So that is the parallel axis theorem. Do you have any questions on this? What is confused? There is nothing to confuse here. See this. Take this particular chalk piece box, I know the moment of inertia of this particular chalk piece box. Suppose if it is rotating about its own axis, that is my finger. So this is holding my finger, right? So this is trying to rotate about its own axis. That means my finger is passing through the center of gravity. So I know the I value. That means I is nothing but the moment of inertia of this body about its own axis like this. Now I wanted to find out the moment of inertia of the same body, but not about my finger. I wanted to identify the moment of inertia of this body when it is trying to rotate a different axis, which is parallel to my initial finger, and then this is rotating this way like this. Now what is the moment of inertia of this particular body, or the equivalent mass that needs to be considered for the rotational energy? So that is nothing but the moment of inertia. So that can be calculated with the help of initial I plus, that is I. That is the moment of inertia of the body when it is trying to rotate on its own. Then plus the mass of this chalk piece box multiplied by square of the distance between initial my finger and my new hand like this. Got it or not? Anjali? Yeah. So this is the moment of inertia calculation with the help of parallel axis theorem and the perpendicular axis theorem. Understood? So to summarize whatever we have discussed today, so that is what we understood, what is mechanics, and then where the question of moment of inertia coming into picture, and then what are the different methods of identifying the moment of inertia. So these things actually we calculate. Now actually let me prove the parallel axis theorem itself. Now we know that the moment of inertia of this is I. So how we got this moment of inertia is nothing but you have considered a random particle at a random location, and then let us say this is the distance r. Then sigma mr square is nothing but the moment of inertia of this body about its own axis. That means I is nothing but sigma m into r square, r. So if the mass is treated as, so sigma m into r square. So this is I. Now I wanted to find out the moment of inertia of the same body, but when it is rotated from this particular axis. That means this mass location about this axis is now this one. So this distance, let us say this is the d, then this will be d minus r. D minus r is the position of the same body. Got it? If it is new position of the same body, then the moment of inertia of the, so I parallel, I call this as IP. So IP is equal to sigma, so m into d minus r whole square, and then this is sigma m into d square plus r square minus 2 into d into r. Now this is sigma md square plus sigma mr square minus 2 times of sigma d into r into m. Got it? So this is sigma md square is nothing but, so d being the constant, then m into d square. This is sigma m is nothing but capital M, which is nothing but the entire mass of this particular body. And then sigma mr square is nothing but the moment of inertia of the body about its own axis, because this is the line which is passing through the centroid. And any radial distance, whatever the particle you have on the other side, the corresponding compensating particle will be there on the left side as well, because this is the center of mass. Understood? So that's why minus 2d times of sigma mr, and this will become 0. Sigma mr will become 0 because this is the positive value of r, this is the negative value of r. So mr1 and minus mr1 on the other side, these two together will cancel out. That's why, because this is the center of mass axis. Got it? So that means this is where entire mass is located. If there is a particle on the right side, obviously there will be a particle on the left side. If there is a particle on the top, obviously there will be a particle at the bottom. So all these sigma mr will become 0. That's why this md square plus I, this will be the parallel. So this is the parallel axis. Understood? Understood or not? Okay. So this is about the moment of inertia. So in the next class, I am going to do certain problems based on the calculation of moment of inertia. Got it? Why 0? I told you just now. Why 0? Sigma mr. Mr means sum of mass into radius, and mass is a scalar quantity. And r actually, so this is on the right side, and correspondingly there will be a left side point as well. So if there is m here, and obviously there will be a small m here. If there is a capital M here, obviously there will be a capital M here. That means if there is a mass on the right side, there will be a mass on the left side. This is positive value of r, this is negative value of r. So sum of all the mass and r product in the entire mass. So for each value there will be an opposite value, right? So the sum together will come out to be 0. Understood or not, Rishi? Right? Because this line is passing through the centroid. That is the condition. So if it is passing through the centroid, then obviously the mass is uniformly distributed about its center, right? So if there is a particle on the right side, there will be a particle on the left side. So these two will be compensated each other in the sigma mr. So that's why this will become 0. So whatever is left over is I parallel is equal to md square plus I. So this is I is nothing but sigma mr square, which is nothing but the moment of inertia of the body about an axis which is passing through its centroid. So that's why this r is counted from the centroid. Clear? Any questions? Any questions? Okay. So if there are no other questions, so I'm going to stop the class for today. In the next class, I'm going to deal with the problems based on this. Yeah. Thank you. Yeah. Good night. Bye bye. So I think so there is no standard books actually that are available for this mechanics topic. So the problem with this is actually none of the books actually you can find out with the Lagrangian and Hamiltonian equations. So but moment of inertia you can find out in Krishna series dynamics book. Moment of inertia, there are many problems which you can solve it. Yeah, Krishna series only for the moment of inertia. And the generalizer coordinates, Hamiltonian equations and Lagrangian equations, for that section you won't find any books. So I have provided in our material by extracting from some of the research papers, so that you can follow in the material whatever I provided. Got it? Okay. D'Alembert's principle and moment of inertia you can follow from dynamics book of Krishna series. Yeah. So thank you. A good night.